So, a warm welcome back to our video lectures on projective geometry. We are in the slot about other geometries, which means that we are going to discover geometric structures like the Euclidean geometry, like spherical geometry, like hyperbolic geometry, as substructures of projective geometry. Last time I gave you a survival package for the complex projective line, and we saw that this is a perfect world to speak about circles, and in contrast to that we know that the real projective plane is the perfect world to talk about lines, points and incidences. And today we want to merge these two worlds to one system that takes the advantages of both worlds into one system. This is a kind of repetition slot for those who already attended the geometrically lectures, but it's also not quite a repetition slot, since the angle from which I approach this topic this time is slightly different from the one that I do in geometrically. So the starting point for today's lecture will be something that I left open in the last lecture. In the last lecture I promised you that I will prove this theorem here, which states, I first read it, that the CP1 cross ratio of 4 points, so you have 4 points in the complex projective line, considered as planar geometric object, so the cross ratio of 4 points in CP1, if they are cocircular, so we know the cross ratio in that case is real, is the same as the cross ratio that we get when we take the same 4 points and consider them on a circle, but now in the real projective plane, in RP2, where the circle plays the role of a conic. And actually, you remember this theorem was the key for understanding that these two maps, the CP1 map that leaves the circle invariant and the RP2 map that leaves the circle invariant, coincide on the boundaries. I hope you remember the animation with the clocks in the two worlds. So, how to get there? Let's first draw pictures. I always think drawing pictures is a good starting point. So, we have a circle, and on that circle we have 4 points, and please consider this picture as the drawing in CP1. If we have those 4 points, we can calculate the cross ratio. In CP1 there is no restriction for calculating the cross ratio. We can take any 4 points in CP1 and calculate their cross ratio. So now we take the same image again, but we consider it in RP2. So this circle here, I've drawn it in a different spot here to make the picture clearer, but think of it as this circle here being really literally the same as this circle, and these 4 points being literally the same as these 4 points. And so now both pictures look the same, and they should look the same as pictures, but conceptually they are different. This here is a picture in CP1, and this here is a picture in RP2. And to distinguish the two worlds, I try to keep a consistent color coding, drawing everything that is in the CP world in yellow and everything that is in the RP world in some kind of light violet. So you have those points, and I told you you can calculate the cross ratio here no matter where your points are. Calculating the cross ratios of 4 points in RP2 is not that unrestricted, so it doesn't make sense to take any 4 points to calculate their cross ratios. We learned that these points must either lie on a line or they must be on a conic, and if they are on a conic, we get a well-defined term of the cross ratio of 4 points on a conic by the following trick. We consider the circle here as a conic. We take some additional point P on the conic, and we can define the cross ratio of the 4 points on the conic as the cross ratio of those 4 points seen from the point P. And we learned in our lectures about the conic that this is indeed an invariant independent of the position of P, so we can really speak about the cross ratio of the 4 points on the conic. Now what we want to do is we want to prove that indeed these quantities that we get here are equal. So first of all, in that world here, we by definition can only get real numbers. So if we have any coordinates of points here and we calculate in these coordinates, well, the coordinates are real, the operations are just plus, multiplication, subtraction and division. They won't take us out of the realm of real numbers. In that world here, it's not that clear that we get a real number, but if we consider the cross ratio here, and we know that the 4 points are co-circular, we know that the cross ratio again will be a real number. So in that world here, in the RP2 world, it's not clear whether we can calculate the cross ratio of arbitrary 4 points. They must lie on a conic or on a line. And in that world here, in the CP1 world, it's not clear that the cross ratio may become real, and it only becomes real if it's on a circle or a line. So that's a good place to overlap those two geometries. So let me make a little bit space here to get into calculations. So first of all, we have to introduce coordinates. So, we have our 4 points in the real projective plane, and I start with, writing down what the cross ratio actually is. So we have 3 by 3 determinants, and we have this expression here. And on the other side, we have 2 by 2 determinants, because we are in a one-dimensional projective space, and we have this expression here. And now we introduce coordinates, and I do that in the standard embedding. I will say a word about standard embedding in a moment. So let's assume that our point A here has somehow coordinates ax and ay in the usual r² plane, and that we have the standard embedding in the projective plane. And we can, without loss of generality, assume that our points are given in the standard embedding, because our cross ratio here doesn't know in which embedding we are. It's invariant under changing the embedding. So taking the standard embedding here is really completely generic without loss of generality step. So how about the complex world? So if this here was the complex plane, the corresponding point here would be at a position with real part ax and imaginary part ay, and I define a complex number as ax plus I times ay. This is exactly the point where I told you that you can overlay the two worlds in a way that these 2 points here really coincide. In one world you get the standard embedding here, in the other world you get a complex number, and from that complex number you get the yellow point A, which lives in CP1, which is again taken at the standard embedding of the CP1 algebraically projective line over the complex numbers. Again, you may ask, is it okay to take the standard embedding, but again with the same argument? The cross ratio is invariant under projective transformations, so it doesn't matter if you take the standard embedding or any other embedding, it will always be exactly the same number. So taking the standard embedding in that case is okay as well. So now we want to perform the calculation. So I've shown you how to proceed with point A, and we do the same thing for points B, C, and D, and for the yellow points B, C, and D. Just the analog construction. So we get a bx, by, and a complex number zb consisting of bx plus I times by, and so on and so on. Okay, let's do the calculation and really check that those two cross ratios are the same. So what would be a good strategy for that? Well, I haven't talked yet about our point P. So P is a generic point, so just any point on our circle here. And a good strategy would be if we find a specific point P of which we know that it is on our circle, so it should be on C, somewhere on this boundary of the circle, such that those expressions that we have in this cross ratio and in this cross ratio agree. And so what I mean by that is that if we take one of the determinants here, say this one, that we get exactly the same as on the other side. So I introduced two variables, x and y, which should just play the role of a, b, c, d as required. So how to find such a point P and how to perform the calculation? There's one important missing ingredient. I want to take this equation here, place in the standard embeddings. So this equation here is not projectively invariant because it's just the determinant on both sides. It's not a projective invariant, but we are in the standard embedding here. And if we prove that for the standard embedding, we are already done because we have seen standard embeddings are a generic assumption here. So let's go and find such a point P. So now comes a little trick. So I just give you a point P. So the point P has coordinates 1, I, and 0, and this point does the job. Those of you who already heard the geometrically lectures will recognize that this point is this famous point I that we had in that pair of I and J. I will talk about I and J in one of my next slides. So let's, for the moment, say that we want to have this point P. So what do we have to prove about point P? So P has to be on the one hand on the conic. This means it has to be on the circle, and on the other hand, it has to satisfy this equation. So let us look at this equation first. So we have our determinant PAB that we want to calculate, and let's simply write down what we get. So we have our point P, which is given by those coordinates here. We have A taken in standard embedding and B taken in standard embedding, and if we expand that term we get this expression. And if you sort and shuffle these letters a little bit, what you get is that this is nothing else as ZA minus ZB times the number I. So just press the stop button and check the validity of those equations here. And if you look at this, this is nothing else as I times the determinant AB. So we almost reached our goal up to a factor I. But this factor of I doesn't really matter because you remember we are calculating cross ratios, and then we divide the product of two determinants by the product of two other determinants, and this common factor here will simply cancel out. So I can say really I achieved the goal that I wanted to have and can make a check mark here. I put it in brackets because we just got it up to that factor. But as I said, this factor won't matter. So what we are left with, we still have to prove that this point P actually lies on the circle. And for that, let me just go back to our very first slot about conics. And in our very first slot about conics, we learned that a generic conic equation looks like that. And if you now do the following thing, that you say, well, assume I have a circle, and this circle has a certain midpoint, and this circle also has a specific radius, then you can write down the equations of that circle and see what this causes on the parameters of the conic. And if you do that, you will recognize that a generic circle equation has this form here. So you have x squared and y squared occurring both with the same factor, and then you have some parameters at the z squared term and at the xz term and at the yz term, and this term here, the xy term, somehow completely vanished. So we have this generic circle equation, and now let's simply plug in our point P. So what do we get? So the x coordinate is 1, the y coordinate is I, and the z coordinate is 0. So everything that has a z simply cancels out because z is 0, and what we are left is x squared plus y squared. And if you look at x squared plus y squared, you have 1 squared plus I squared, which gives a nice 0. So we can say this point P here lies on any circle. So this is a kind of amazing thing. So this point P here, we didn't put in any parameters of our circle equation here. We just took one point with fixed coordinates, and we just find out this point here really lies on an arbitrary circle. So all circles pass through that point, and with those two statements here, so we get the equality of the determinants and P is on the circle, we finally finished our job, that we actually proved that these two cross ratios are indeed the same. And you remember, this was the key for making projective transformations on the boundary of the circle agree in both worlds. We will need that fact later when we are talking about hyperbolic geometry. So this will be a key ingredient of when we are talking about hyperbolic geometry. So, but we did much more. We introduced this point P, and we have shown that these two expressions here agree, and we found a point P on all the circles, and this is where a new journey starts. And this point P in the literature is usually not called P, it's called I, and it comes along with a companion with a point J, which has essentially the same properties. So the point I is our point P, and the point J is just the same point with one difference. You replace the occurrence of I by minus I. And these points have the great property, these 2 points lie on all circles. So you can do the calculation with J as well that we did on our last slide and see, well, it also lies on all circles. You can even go further and say, well, circles are defined as those conics passing through I and J. So look at that picture here. We had that picture before, but here now we have the slight difference that I have points I and J. I marked them but by such a kind of little cross, indicating that you don't really see them in the pictures. They have complex coordinates, so you cannot really draw them. But symbolically, they lie on a circle, and we claimed, well, 6 points are on a conic if you see them at the same cross ratio from 2 points on the conic. And let me just look what it means that the cross ratios are the same. If I calculate that cross ratio here, we already know we get the cross ratio of the corresponding complex points in CP1. If I, instead of I, use J at that place, then what happens is that I get the cross ratio conjugate. So I replaced I by minus I, and by that I replaced this number by its complex conjugate. So this equation here reads in the following way: this number must be equal to its own complex conjugate, which means it must be real, which tells you that our complex cross ratio indeed is a real number, and by that we can really say a circle is a conic through I and J. So, let me try to draw a picture of that situation. And actually it's close to impossible to draw a correct picture of that situation, because we have complex numbers involved, and proper complex numbers do not live in our real space. So one picture you might draw is the following here, that you say, well, you have those 2 points and I don't see them. That's the reason why I mark them here as a kind of red cross, but they are still on every circle that you have. On the other hand, you can consider the 0 here and observe, well, if they have a 0 in the last spot here, this means they are on the line at infinity. So a different picture that one could draw is to say, well, those 2 points are the intersection of the line at infinity with our circle. But, well, a circle and the line at infinity don't intersect properly. So no matter how I do it, there will be something a little bit cheesy in that drawing. But let's consider it in that way. Point I and J are on the line at infinity, and we at the same time assume they are also on the circle. Why did I draw this little picture here? Because if you look at it, this is a dual degenerate conic. So it's a line, you can consider it as a double line with 2 points on it. And actually it's not only a dual degenerate conic, it's a complex dual degenerate conic. And you may remember our classification of all possible conics, where we saw that, well, there is one spot, this spot here, where we really get this situation that we had now. And there are 6 other spots. And we will see that this spot here corresponds to our usual Euclidean plane, and the other spots correspond to other geometries. Before we go along that path, let me just give you a few more interesting statements about I and J. And next thing I want to consider is cross ratios in relation to I and J. So we know I and J are on the line at infinity, so we may take 2 other points at the line at infinity and calculate the cross ratio, and we may ask, what is this cross ratio? So let's first of all introduce again some coordinates. Let's say A has coordinates ax, ay, 0, and that B has coordinates bx, by, 0, and then we can write down the cross ratios we get. We get these expressions here. So the product of two determinants divided by the product of two other determinants. You may wonder why I've written 2 by 2 determinants here. Well, actually, you see you have a 0 in the last spot, and all those points are collinear, so you can retract to the line at infinity to do these calculations, and what you get is exactly that. If you write down what these determinants are here, what you get is the following expression here: complex number times another complex number divided by the complex number conjugate divided by the other complex number conjugates. And we may wonder, what are these complex numbers? And for that, assume now that L infinity is really infinitely far away, and that you are given two lines through these points A and B. So A and B are very far away, and you are drawing a line through A and a line through B, and this means you fix two lines from two bundles of parallels. And these bundles of parallels have a direction, and we can well, specify this direction by the normal vectors of these lines. And it turns out that these normal vectors are exactly the two-dimensional vectors you get from the coordinates of A and B by switching their position and adding a minus here. So you see the orthogonality already immediately. If you multiply that by this here, you see these are orthogonal vectors. So, and this here now again looks an awesome lot like the complex numbers we have here. We just have to turn these vectors here into complex numbers. So we define a number set A and we define a number set B in a way such that we simply take the coordinates of our point and make the real and imaginary part of our complex numbers here. So if we rewrite that, we get the following expression here, which is an interesting one. So you get set A divided by set A conjugate times set B conjugate divided by set B. And this has a nice implication. First of all, set A and set A conjugate has the same absolute values, the same lengths. So the length simply cancels out for both A and B. What you're left with is just a complex number on the unit circle, so it can be written as some e to the power of something, and the power of something that you get here is actually, since you divide here, the enclosed angle between your two vectors. You have to be a little careful because you have this angle happening twice here, because you have set A divided by set B and set A conjugate divided by set B conjugate. So you get twice this angle here. And if you look at that drawing, this angle here is the same as the corresponding angle between the lines. So, as I said, those of you who heard Geometriekalküle will remember some ingredients of this lecture here. So what we arrived at is a formula to calculate the angle. So we got, after all, this nice formula: the cross ratio of A, B, I, and J is the same as e to the 2I alpha, where alpha is the enclosed angle between the two lines. Or if you put it in a different formula, it's just you can calculate alpha by taking two lines, taking their intersection with the line at infinity, taking the cross ratio of these 2 points with I and j, and taking the logarithm of that and scaling down by 1 divided by 2i. This formula will be our starting point for defining way more general situations that give us the description of a really large variety of different geometries. So from there we will go to our next starting point of so-called Cayley-Klein geometries, which is the general term for such kind of geometries. Let me finish by collecting still a few facts. So in particular, you get a 90-degree angle here if your 4 points A, B, I, and J are in harmonic position. So if you take all that together, you can say, if you want to do Euclidean geometry, you can do essentially everything you want to do by doing projective geometry and introducing I and J. So you get, for instance, circles in Euclidean geometry are conics through I and J. We have seen orthogonality and angles can both be carried out by this construction. Take two lines, intersect them with a line at infinity, take the cross ratio, take the logarithm of that, and make statements about that. You can also make advanced geometric constructions, like for instance constructing reflections. Here is a construction of the situation where you have a point P and a line L, and you want to construct the mirror image of P to the line L, and you can completely do that with I and J, and I really invite you to read the corresponding chapters about doing elementary geometry with I and J in the Perspectives on Projective Geometry book. Here I put a few dots here. This story continues and is extremely exciting. So you could say Euclidean geometry is projective geometry together with I and J. And from there we will embark to more general properties where we say, well, da-da-da geometry, da-da-da may be hyperbolic, spheric, relativistic, or other things, is projective geometry together with a certain conic. We will have that in the next lecture. See you there.